This video covers Friedel-Crafts alkylations and acylations. We'll start first with alkylations. A Friedel-Crafts alkylation is one in which we use an alkyl chloride and aluminum trichloride to instill an R group onto a benzene ring. This works with primary, secondary, and tertiary alkyl halides, although we'll see an example where primary alkyl halides have an added complication. Let's look at an example with 2-chloropropane. In the first case, what happens is an acid-base reaction to form this Lewis acid-base adduct. Then the chlorine departs to form a secondary carbocation and aluminum tetrachloride. This secondary carbocation is a great electrophile, so what happens next is that the benzene ring attacks it, forming the arenium ion, which is then re-aromatized by reaction with aluminum tetrachloride. Again, we're following the same electrophilic aromatic substitution pattern. It's another EAS reaction. But what if the alkyl chloride is primary? Then we get a different outcome. Here we have a 1-chloropropane, and while we do see a propyl group in the product, we also see an isopropyl group in the product. How does this happen? Well, you know that you can't form a primary carbocation, so a different mechanism has to be in play when we install the primary carbon directly attached to the benzene ring. So here we have the reaction to form the acid chloride adduct, which I've skipped the step to form, and the benzene ring is going to attack that directly to form the arenium cation. And then aluminum chloride is going to be used to remove a proton and re-aromatize. So that's how we get to the product without rearrangement. But how do you get to rearrangement? Well, when you're at the stage of having this Lewis acid-base adduct, you can have a hydride shift to form a secondary carbocation, and that's what reacts with benzene to form isopropyl benzene. This reaction also works with tertiary alkyl halides. For example, here's tert-butyl chloride reacting with aluminum chloride, and we get tert-butyl benzene. And this does not undergo a rearrangement because the tertiary carbocation is the most stable. It's also important about this reaction to note that polyalkylations can often occur, and this is whether the alkyl chloride is primary or secondary or tertiary. This polyalkylation is a problem even if you don't have an excess of the alkyl chloride, and that's because the activated aromatic ring results from the installation of an alkyl group. So what does this mean? So let's say that we have tert-butyl benzene, and it's in a solution with benzene, and it's in a competition of whether this is going to react with the tert-butyl chloride, the carbocation that results, or is benzene going to? And here we want to look at the carbocation intermediate that forms. So this is if that tert-butyl benzene reacted with another tert-butyl cation. This cation is more stable than this original one where benzene had reacted with one carbocation of the tert-butyl group. So because this is more reactive than benzene, then we're going to get polyalkylation. So this is always in competition. These reactions always give a mixture of products. Some other notes about the Friedel-Crafts alkylation is that there's no reaction when you have a vinyl chloride and no reaction when you have a phenyl chloride, and that's because their carbocations are unstable. Also, reactions don't occur when strong electron withdrawing groups are attached to the ring. So let's say that you've got nitrobenzene, and we all know that nitro groups are very electron withdrawing. So they're so electron withdrawing that this alkylation does not occur. This is because the nitro group's electron withdrawing nature destabilizes the rhenium cation. So we want electron donating groups to stabilize the rhenium cation. Nitro groups are no good. Let's do a practice. Let's predict the product of the following reaction. And what I'm going to tell you is that the product is, let me draw it in red, the product is not this. You might see it as a minor product. So let's just draw that that is minor, possibly. So the first step of our mechanism is to form this Lewis acid-based adduct. And then remember what can happen with primary alkyl halides is that we can get a rearrangement. And that's what happens here, is that we get a methyl shift. And now we form this carbocation, and this is what reacts with our benzene ring, this tertiary carbocation that is more stable. Let me draw that arrow around here. That looks better. Then we get re-aromatization. And this is our product. So always keep that in mind when you have a primary alkyl chloride, that rearrangement is going to occur. Alkylations can happen in other conditions. How is this going to work? We've got a reaction of tert-butanol and sulfuric acid, and we form tert-butylbenzene. So this is not a Friedel-Crafts alkylation, but it's still an alkylation. So I want you to take a minute and pause the video and see if you can figure out how this reaction works. Let's start with the tert-butanol. You know that whenever you have sulfuric acid present, you're also going to have water, and therefore you have the hydronium ion, and that is going to protonate tert-butanol. And then in the second step, water leaves as a good leaving group, and you have the tert-butyl carbocation. Then just like when we did in a Friedel-Crafts alkylation, our benzene ring attacks that tert-butyl cation, and then we can use a molecule of water to remove that proton and re-aromatize our ring. So that's pretty nifty, right? Next we're on to Friedel-Crafts acylations. So we're switching from putting an alkyl group on to putting on the second half of a ketone. In this case, we also use aluminum chloride to activate our acid chloride. So we're forming this Lewis acid-base adduct. And then that falls apart to form the acylium cation. And this is a very good electrophile. And benzene reacts with that to form the iridium cation intermediate. And then aluminum chloride takes away a proton so that we form our aromatic ring again. This reaction, unlike the alkylation, is not subject to multiple acylations because the first carbonyl destabilizes subsequent iridium cations. If you get a ketone that's at the benzylic position, you can undergo a reaction called the Clemmensen reduction. And that's a reaction where we take a zinc-mercury amalgam and hydrochloric acid and heat it. And what this does is removes this carbonyl carbon so that we have 2 hydrogen atoms in its place. An example is shown below where we have this acid chloride and we are able to install the carbonyl, which then is reduced to form this sec-butyl chloride, or sec-butyl benzene. And why this is useful is that we were able to install a primary carbon at this position without being worried about whether we're subject to rearrangement in the Friedel-Crafts alkylation. So in this way we can make products with alkyl groups that are primary in a way that we can't do with the alkylation. In our last slide, we're going to do a practice. The following compound cannot be made by a Friedel-Crafts alkylation or acylation. Why not? I want you to pause your video and think about this, then come back in a minute. Well, we know that we can't do an acylation because we have a secondary carbon here, and we can't put a carbonyl there because we would violate the octet rule. So the acylation is easy, that's out. Let's look at what happens if we try to do an alkylation at that carbon. So what we would need is to have the following alkyl chloride, and we would treat that with aluminum chloride. Then we would have the aluminum tetrachloride leave, and we'd get this secondary carbocation, and we can see that this is subject to rearrangement. And we would get this carbocation, and then skipping a few mechanistic steps, that would end up with us forming this product. So that's why we can't make the following alkyl benzene via an alkylation or an acylation. We'll have to find another way to make that. That's the end of this video.